Power. Power is the rate at which work is being done. Acacia, in physics, anytime we say the rate, what we really mean is you're dividing by time. Our symbol for power is capital P, not lowercase p. What's lowercase p, our abbrev for? Momentum. Uppercase P, power. And I just told you, since it's a rate, it means we're dividing by time. It's work divided by time. If you're exercising and you're getting tired, it's not because you're doing work. It's because you're generating lots of power. Power causes tiredness. Did I give you power equals work times time on your green sheet? That's my way of saying, can you all look and see and make sure you know where it is on your green sheet? I think it should be probably right next to force times distance, I hope. Yes? Okay. What would the units be for power? Well, what are the units for work? Per. What are the units for time? Power is measured in joules per second. But this is such an important concept, we've given a joule per second its own name. Power is measured in watt? Watt? Watt is power measured in? Emilio, watt? Watt. Power is measured in watts. Symbol capital W. And this leads to a bit of a problem, because capital W, when it's on the left-hand side of an equal sign, that's work. Capital W, when it's next to a number, that's watts. And I've mentioned many times, we don't have enough letters to go around. We don't. You'll just have to read very, very carefully. Don't mix up watts and work. Watts are named after James Watt, who I think is the most overrated science person to have such an important unit named after him. I really wish they'd named it after somebody else. He's overrated. Much like LeBron. Anyway, he's overrated. Okay. Power is also a scalar. It has no direction, much like your future. It has no direction. Example 1. I like example 1. An electric motor is used with a pulley and a rope to lift. Lift to me is a bit of a trigger word. I would mentally underline that. A 650 Newton load from the road up to a height of 12 meters. The job is done in a time of 12 seconds. What's the power output of the motor? Madison, what's this question asking me to find? What is the? So I would probably start out by going, well, power is work over time. Did they give me the time in seconds? Yes. What? Yes. So it's going to be over 10. What about the work? What word did I underline, Madison? The work done in lifting. Who remembers what was the work done in lifting? We derived kind of a special sub-equation for force times distance for the work done by lifting. Who remembers? We may have added it to our green sheet. I don't know. MGH. Okay? So I'm going to write MGH over 10. Did they give me the mass in kilograms, Madison? What did they give me? Which is another word for, starts with the letter W, but it's not work. No now. No now. What was mg? They gave me the weight. I'm just doing some review. I know. Again, we got lots of W words. I know. Sorry about that. But they gave me the weight. So I'm not going to go 650 times 9.8. I'm just going to put in the 650 for mg. If I wanted the mass, I could divide by 9.8. But what's the height? Yep. Are you ready? Which is what? $650 times 12 divided by 10. Should work out dead even. No decimals. What'd you get? 780. Even? 780. Power is measured in watt? Okay. That is the SI or metric unit for power. Watts. There is another unit for power. It was invented by James Watt. It's stupid, but it's still used. It's the horsepower. 1 horsepower is about 750 watts. You don't need to memorize that. I'll give you the conversion factor if you need it. If you're being fussy, I think it's 749.8. It's 750, close enough. So the motor in this example would have a horsepower of, well, a little more than 1, but I'd like to be more specific. Let's do a unit conversion. Now we're coming to the end of the year. I'm reviewing stuff from all year long. Whenever I did a unit conversion, what was the first thing I always did? Wrote down what they? I'm going to write down 780 watts. And then, Jada, we said you can multiply by a fraction. I want watts to cancel, so where is it going to go in my conversion factor? On the... And on the top, I'll have horsepower, and it looks like 1 horsepower is 750 watts. And this answers the question, Jada, do I times by 750 or divide by 750? How do you know I times by 750? Where is the 750? On the... So am I timesing or am I dividing by 750? What was that? Divide. It answers the question for me. I've never bothered memorizing all the strategies. I can figure it out in 1 line. What'd you get? It's going to be 1 point something. $1.04. Anybody else? Yeah? Horsepower. Yeah, a little more than 1 horsepower. What a stupid unit. I'm going to go on a rant, but later. Example 2. A 60-kilogram girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. The stairs behind my left shoulder back there, the ones over here, they're right around 3.3 meters high. All of you have a mass around 60 kilograms, some more, some less. But I'd like you to imagine doing those stairs in 2.6 seconds. Are you walking slowly if you're doing the stairs? Are you sprinting as fast as you can? No, this would be hustling up the stairs. Just to give you an idea of what's a lot of wattage, Ella, and what's not. Ella, what does example 2 want me to find? Well, power is work over time. Ella, how much time? Good. What about the work? Ella, when you climb a flight of stairs, what force are you doing work against? So you know what? This is the same as lifting your body up the stairs. How do I calculate the work done by lifting? Oh, okay. So it's going to be 60 times 9.8 times 3.32 all over 2.6. Ella, what'd you get? 700, I'll call it 751. Power's measured in watt? Good. If 1 horsepower equals 750 watts, what's her power output in horsepower? Almost exactly 1 horsepower. In other words, all of you are capable of putting out about 1 horsepower for a reasonable amount of time. I could probably get you to hustle up 4 or 5 flights of stairs before you would need to stop and rest. So you're capable of putting out 1 horsepower. What is 1 horsepower? Eric, it's a stupid unit. The horsepower was originally defined by James Watt, for whom the Watt is named. Some people will say he invented the steam engine. If he had invented the steam engine, he would be worth having a unit named after him. Clearly, he didn't invent it. He improved it. What he really was a good marketer. He had these improved steam engines, and he wanted to sell them to farmers. And so he invented a unit called the horsepower. And he would say to a farmer, this steam engine is 2 horsepower. What does the farmer immediately think? This steam engine does the same amount of work as what? 2 horses. Totally made up. He did not do calculations to figure out how much work a horse was capable of doing. But it was a brilliant advertising move. Farmers bought it. In fact, it caught on so much, we still measure car engines in horsepower. What a stupid unit. Do any of you know how much work a horse is capable of putting out in an hour or in a second? No. But we still measure engines that way. Dumb. Dumb. But because it is such a dominant unit, almost any engine, unless it's an electric motor, will be measured in horsepower. Electric motors are more and more being measured in watts, thankfully. But horsepower, okay. I like example 3. I like example 3. Example 3 is a nice question. Ooh. Scott, what's example 3 asking me to find? How long it takes. Which physics concept or variable do you think that wants me to find? Time. Okay. We have found time in many ways. It showed up in VF equals VI plus 8t and D equals V at t. Let's keep reading. They gave me 10 horsepower. We're lifting. You know what? I think I'm going to use power. What's the power equation, my friend? P equals? That's, I told you need to look at your green sheet and find it. That's, yeah. Say it again. You're right. Okay, let's write that down. What did you tell me this wants me to find, Scott? I want to get the t by itself. Where is the t right now? On the... Bleh. Wait a minute. Dividing by t on the right, that's the same as timesing by t on the left. Let's all do that. So now it's t times p equals w. How would I move the p over to get the t by itself, Scott, my friend? Yet another equation for time. I'm not going to memorize it. Time is apparently work divided by power. Hand it in face down. Thanks, Bryce. Got a bit of a problem, though, Scott. We don't do physics with horsepower. So let's do a little bit of a conversion. 10 horsepower. I guess I want horsepower on the bottom. I want watts on the top. It's going to be 750 watts is 1 horsepower. Scott, Jada, am I going to times by 750 or divide by 750? In your head without a calculator, what's 750 times 10? When you multiply by 10, what do? Just add another? Okay, so power, which is 10 horsepower, it's going to be 7,500 watts. That's what's going to be on the bottom. Scott, do you see which 4-letter word we should have underlined? It starts with letter L. What's the work done by lifting? Oh, so you're telling me it's just going to be mg8. Yep. So m, 500, g, 9.8, h, 30, all over that. How long will this job take? Units, it's time. What if you need it done faster? It's impossible. You need to get a more powerful motor. Now, Eric, this is kind of a trivial example, but someone wants to make sure their phone is on silent. I think I'm having a little deja vu. You're not that important. Don't even need to read it. Put it face down. There you go. Get up. Thank you. This is kind of a trivial example, but how many of you have seen those massive skyscraper cranes that they use in Vancouver to build skyscrapers, those big ones, okay? You can actually calculate pretty accurately how much mass you're going to be lifting to what height for each floor. You can calculate pretty accurately just how much time it's going to take to lift all the materials to the right height. Oh, and if it doesn't work, if you need to do it in less time, you can say we need to hire a second crane or we need to get a more powerful crane with a more powerful motor. And they do that. It's a bit more complicated because the height is changing as you're building higher and higher, and so it involves some calculus, but occasionally it's the same concept. You can calculate how much time it's going to take you to get the materials in place. And they do that for projects all the time. 1 watt is pretty small. It's 1 joule per second. It's not much at all. So power is also measured in kilowatts and megawatts. You may hear about dams being built, hydroelectric dams or power stations or nuclear power plants, and they'll say they can put out thus and such many megawatts, this many million joules per second. So 1 kilowatt is 1,000 joules. You times it by 1,000, or if it's in kilowatts, divide by 1,000. Megawatt times by 1,000,000. Turn the page. Light bulbs are measured in watts. You're just at the generation which is probably starting to swap out the old incandescent bulbs for LEDs. How many of you still have the old incandescent bulbs in your house, the ones that get really, really warm when you touch them? Okay? Never replaced a light bulb. Ooh, aren't we special? Those are measured in watts. The power of a light bulb is how much electrical energy it consumes in 1 second. If you're wondering, how do you get work out of that? You're moving electrons through a circuit, force times distance. You are. Okay? A 40-watt bulb, for example, uses 40 joules of energy in 1 second. A 60-watt bulb uses 60 joules of energy per second. What's the power rating of a bulb that consumes 4,200 joules of energy in 70 seconds? Zaina, what's this asking me to find? Well, power is what? There you go. Zaina, what's the time? Good. How much work? Well, work is measured in joules. I didn't actually use the word work. I gave it to you in terms of electrical energy, but that's the amount of work. 4,200 joules. How many watts is this particular light bulb? Should work out dead even. I tried to make this one work out. Which is a pretty standard room bulb. Oh, Ella. Typically, Ella, if you actually replace a light bulb, you'll find most of them are 60-watt bulbs if they're the incandescent ones. They use 60 joules per second. Sometimes you'll see a 100-watt that needs to be really bright. Those ones get really, really hot, though, to touch as well. And you can even get bulbs that are brighter. Some of you may have had as a kid an easy bake oven. That's just a light bulb oven. I think it's a 150-watt bulb in there, and it's just throwing off a lot of heat. Appliances also have power ratings. So a microwave is rated at 1.2 kilowatts of power. It's running for 6 minutes. Ooh. Jonah, what's this want me to find? Work. What's this 1.2?
Kilowatts.
More specific as a physics concept starting with the letter P.
Power.
What's this 6? But the units suck. Okay, so let's make a little note. Power equals 1.2 kilowatts. How do I go from kilowatts to just plain old watts? It's going to be something to do with a 1,000. Times or divide? So you're telling me, because otherwise that would mean if it was divide, 1.2 kilometers would be 0.0012 meters. I think not. And by the way, don't feel bad. This is how I often, because I haven't memorized it, my first thought would have been, well, if I divide, I get a stupid answer. It's got to be times. Okay? I haven't bothered memorizing it. So it's going to be 1,200 watts. Yes? Okay, and time, well, that's 6 minutes. How do I convert minutes to seconds? It's going to be something to do with a 60. Yep. How many seconds then? I don't think 6 minutes is 60 seconds. I think 6 minutes is more than 60 seconds. I think 1 minute is 60 seconds. 360. Good. Okay. And now we can solve this. Power is work or energy times time. You've told me we want to get the work or the energy by itself. How? How will I move the T over? What's the T doing to the W? Work is power times time. Yet another definition. Don't need to memorize it. This is why I'm teaching you to derive these things. So it's going to be 1200 times 360. $432,000 joules of energy. Is that a long time to run a microwave? 6 minutes? Not really. You would probably do that more than once a month. So your parents, BC Hydro, charges your parents for how much energy they use. But BC Hydro does not give them their bill in joules. If they got their bill in joules, it would terrify them. BC Hydro gives them their bill in kilowatt hours. I think I talked about kilowatt hours during the work lesson. 1 kilowatt hour is 3.6 times 10 to the 6th joules. How many kilowatt hours does this use? I guess I'm going to do a unit conversion. Write down what they gave me. See, a typical household uses several 100 million joules of energy per month. And parents, to receive a bill that had several 100 million on it, they would be terrified. And also, those numbers are too big to wrap your brain around. Remember at the beginning of the year, I showed you a website with a whole bunch of pennies, and we've figured out pretty quickly our minds just did not scale up to large numbers. So instead, BC Hydro and almost any electric company on earth, they convert joules to kilowatt hours, which, by the way, is power times time. Power times time. It's still energy, just a different unit. I guess I want joules to cancel. Kilowatt hours on the top. 1 kilowatt hours is 3.6 times 10 to the 6th joules. Jada, what am I going to do with that 3.6 times 10 to the 6th? Yep. You don't need to memorize this conversion factor. If you need it, I'll give it to you in the question. And I get 0.12 kilowatt hours. That's a much nicer number for adults that don't have a strong math background to deal with. They're used to dealing with dollars and cents and decimals, and so that's in their wheelhouse. I wrote here, kilowatt hours is a measure of energy, not power. So here's some bad physics. I think I have a photo here. I think. Yeah. I saw this on I think a SkyTrain station. They posted this. BC Hydro had posted this. Burn calories, not kilowatts. That says burn energy, not energy. No, that says burn energy, not power. Those units don't match. Calories is a measure of food energy. Kilowatts is a measure of power. It should say something different. To me, it should say burn calories, not kilowatt hours. Burn food energy, not electrical energy from the grid. Take the stairs. Bad units. Eric, you notice those things all the time, right? Yeah, they drive me cray-cray. Question, Ella? Good, okay. I think we're almost done. Yeah, a couple more, we're done. A hot dog takes 40,000 joules of energy to cook. If a microwave is rated at 800 watts, how long will it take to cook a hot dog? Huh. Fahim, what's this question asking me to find? Okay. You know what? Let's do my old reliable T equals question mark. I mean, that's never let me down in a long time. What's that 40,000? How do you know? Worth memorizing units. I'm already thinking, hey, I only have one equation with work and time in it. Let's keep reading. What's that 800? How do you know? Power's measured in a watt? Yeah. How can I figure out the time, Fahim? Yeah, so power equals work over time. Scott, where is the T on the bottom? Yeah. Move the T to the top and divide the P over. Yes? It's going to be 40,000 over 800. How long will it take? 50? I think 50 seconds, yeah? By the way, if you're nuking a hot dog for 5 seconds and then biting it, it won't be pleasant. Okay. 50 seconds. Well, microwaves kind of come in two varieties. There's the smaller ones you may have seen. Those are typically around 800 watts. Then there's the larger ones. The larger ones are usually around 1.2 kilowatts or 1200 watts. How long would a large microwave take to cook this hot dog? Well, time is still going to be work over power. It's going to be 40,000, but this time divided by 1200. How long will this take? $33.3 repeating? No. Yeah? No, maybe. Is it 33.3 repeating? Yeah. And because the company does not know which type of microwave you're using, this explains why it always says on the back of a microwave package, microwave oven times may, you've all seen it, what? Have none of you cooked anything by looking at the instructions for a microwave? It always says on the back, microwave oven times may vary. Yeah, they don't know what kind of microwave you're using. They don't know whether it's an 800 watt that can put in 800 joules per second or a 1200 watt that can put in 1200 joules per second. There's a special subcase of the power equation if you were moving at a constant speed. Can all of you write down power equals work over time? But Acacia, work is what times what? On your green sheet. Force times. What does D stand for? You know this. Help her out, Ella. Yeah. Okay, so this is the same as force times distance over time. Yes? And then all of you, can you circle the D over T? Acacia, redeem yourself. What are the units for distance? Meters. What are the units for time? Second. What is meters per second? Because that's what I've circled. What do I measure in meters per second? You all know this. Someone said acceleration. What's acceleration measured in? Meters per second. Okay. So what do I measure meters per second? We're in Scalarville. What's the scalar version of velocity? Starts with letter S. Speed. Okay. Another special way to calculate power is force times constant speed. Did I give you that version on your green sheet as well? I can't remember. I think I did. I didn't. Sorry. If you want to, next to work over time, you could write it as power equals work over time equals force times speed. When do I use that? If they ask me how much power and they give me no time, but they give me a speed. Like, example 7. How much power are you generating if you need a constant force of 32 newtons to overcome air resistance while pedaling your bike at 12 meters per second? Okay. Cole, what are they asking me to find here? Yep. Don't write this down, look up. My first thought would be, Cole, power is work over time. That's my go-to. Do you see a time in seconds here anywhere? Do you see work in joules here anywhere? Pick your pencils up. My next thought would be, well, there's another special subcase that pops out of that equation, force times speed. Did they give you a force? What? Did they give you a speed? Zaina, what'd you get? I saw you typing. 384. Power is measured in watt? Power is measured in watt? Watts. Okay. next bit is meant to be Captain Obvious, but it also explains something you may have noticed as a kid. If you want to go faster, will that take more power or less power? If V gets bigger, what happens to this answer? Okay. Also, what happens to air resistance as you speed up? So both of these get bigger. So, be obvious. If you want to go faster, will that take more power or less power? Okay? So, does pedaling faster make you more tired or less tired? This is why I said power is tiredness. But it's more noticeable than that. As V gets twice as fast, air resistance also gets twice as big. So to go twice as fast, you're going to need 4 times the power. You're going to get 4 times more tired to go twice as fast. This is why, if you've ever pedaled a bike, getting going fairly fast doesn't take much effort. But to get going really fast takes way more effort than it took you to get going pretty fast. That's why, right there. You've all noticed that, I hope, right? Riding your bike. Going pretty fast, not too bad. You can do that barely working up a sweat. But to add that extra little bit, holy smokes, you got to give her. Oh, if you tuck, you can reduce air resistance a little bit, a little less tiring. Now we've just explained the Tour de France. So how could a cyclist go faster but use less power? Tuck. Reduce air resistance. And I probably said this before, but if not, I'll repeat myself. Any professional cyclist, like in the Tour de France or in the Olympics, they've spent hours in a wind tunnel. They have memorized for their own specific body what the most aerodynamic tuck position is. And they've committed that to muscle memory, because everyone's is going to be a little bit different. One person's shoulders might be a bit broader than someone else's, or one person's hips might be there. You memorize your own position, and they commit that to memory, and that's their tuck position. Anybody here do competitive cycling? I should have asked. Heck, some of you can't even change a light bulb. You know the joke I'm wanting to ask, right? How many Ellas does it take to change it? Okay, we won't go there. Apparently more than one, though, right? Yeah, there's our answer. What's your homework? Try number 1. Underline the word lifts. How many pieces of luggage are you lifting in this question? Read the question. 42. What's the mass of 1? What's the total mass? I think the M is going to be 42 times 24. There's your time. Oh, minutes. You have to convert that to seconds. Okay. 2 is good. 4 is good. I didn't give you the conversion factor for horsepower. It's in your notes. On a quiz or a test, I would give you the conversion factor. I think it was 1 horsepower is 750 watts, but it's in your notes. You can skip 5. 6 is good. 7 is good. 8 is good. Skip 9. 10, but you can cross out part B. I haven't done efficiency yet. That's going to be tomorrow's lesson.